Operational amplifier is a differential mode amplifier and it contains multi-stages of C amplifier. The short form of operational amplifier is OPAMP. OP-AMP. OP stands for operations. Now, what are the operations that we hint to? They are the mathematical operations like addition, subtraction, integration, differentiation, finding out logarithm and so on. So, with the help of OPAMP, it is possible to do these mathematical operations and hence it is known as OPAMP. Operational amplifiers. As we discussed, it is a high gain multi-stage amplifier. It can do mathematical operations like addition, subtraction, integration, differentiation and so on. The input stage is a differential amplifier. We will discuss this term later. In short, differential amplifier means the difference between the two input terminals is taken as the effective input of the amplifier. So, that is the differential amplifier. So, first stage is the differential amplifier. Then the last stage, it is a push-pull amplifier. You know what is a push-pull amplifier? It is a class C amplifier. Two complementary amplifiers, transistors will be used in a push-pull manner, that is the push-pull class C amplifier. Now, the next point is, it is an direct coupled amplifier. That is, the intermediate stages of an OPAMP are direct coupled. Direct coupled amplifier. What do you mean by direct coupling? One stage of amplifier is connected to the next stage directly. The collector of one stage is connected to the base of the next stage without any transformer, capacitor or any other coupling device. So, it is called as direct coupling. Because of the same reason, we can also use this OPAMP for amplifying the AC and DC signals. So, because of the direct coupling, it can be used for amplifying DC and AC signal. Now, the next important point is that OPAMP has got a very high input impedance. So, it has a very high input impedance and a very low output impedance. So, we discussed that the input stage of an OPAMP is differential amplifier. The intermediate stages are direct coupled multi-stage amplifiers and the last stage is class B push-pull amplifier. So, finally, you will get a high output from this OPAMP. As I had said, we will just have a look at what is differential amplifier. Just an overall idea. In the differential mode, you will have two inputs. That is, you have two transistors, two bases. This is input 1 and this is input 2. So, difference between the two input terminals will be taken as the effective input for this amplifier unit. And if you are taking differential output, the difference between the two collector potential will come out as the effective output. So, this is the differential mode. One thing to be noted here is, here this is plus VCC and this is minus VCC. It is not in fact the ground. I mentioned it as minus VCC. That is, you require a dual biasing here. A dual biasing means If we are using an op-amp IC741, you will need a plus 15 volt plus VCC and minus 15 volt minus VCC. It is not the ground, but it is minus 15 volt. So that is the concept of dual biasing that is required for IC741. So now let us discuss about an ideal op-amp. You expect, or theoretically you can say, an ideal op-amp has infinite gain. That is, gain is very high. When speaking of the practical case, it is not possible to have infinite gain, but you will have a very high voltage gain of the order of 10 raised to 5. You will have a gain in the order of 10 raised to 5. So that is a very high value. This is a voltage gain possible for a op-amp. Then the next property that you would assign for an ideal op-amp is it has infinite input impedance. This is also ideally, so practically speaking, you will have a very high input impedance of the order of kilo ohm or hundreds of kilo ohms, you can say like that. So it will have infinite input impedance. Then the other property that you can assign is it has zero output impedance. This is also ideally, so practically you can say your output impedance will be in the order of a few hundred ohms. So it will be in the order of hundreds of ohms, but not in the order of kilo ohms. Now you can speak of one more property for an ideal op-amp. It has infinite bandwidth. You know what is bandwidth? That is, if you draw a frequency response curve for a CE amplifier, you know what is FL and FH. This is a frequency response curve, and this is known as the bandwidth of a CE amplifier. When it comes to op-amp, especially ideal op-amp, this bandwidth becomes infinite, or you expect an ideal op-amp to have a frequency response like this, so that its bandwidth is infinite. Now coming to the practical case, you cannot expect an infinite bandwidth, that is a constant gain for throughout the frequency, but you can expect a high bandwidth for a practical case. So this would be the bandwidth for a practical op-amp, though for ideal op-amp it is said to be infinite. So we found what is an operational amplifier, what are the operations it can do, what is an ideal op-amp, what are the characteristics. The characteristics as it has infinite gain, it has infinite bandwidth, infinite input impedance and zero output impedance. We saw that the input stage is a differential mode, intermediate stages are direct coupled, output stage is a push-pull class A amplifier. Then we discussed that it is possible to amplify AC signals as well as DC signals with the help of this op-amp. The practical gain of this op-amp comes in the order of 10 raised to 5. Coming to the symbol of op-amp, this is a symbol of op-amp. There should be a plus VCC biasing. if this is IC741, then we will give a plus 15 volt VCC and minus 15 volt VEE. The two input terminals are V1 and V2. We have already discussed that we give a differential input. So, there will be two inputs V1 and V2, and the output is V out. So, minus sign shows that this is the inverting input. We will discuss what is that, and this input is known as non-inverting input. If you give a voltage in this non-inverting input, it will appear as non-inverted or in the same phase in the output. But if you give an input at the inverting terminal, then it will appear out of phase in the output. So, that is the concept of inverting terminal and non-inverting terminal of input. So, to understand the concept of inverting and non-inverting, let us try this. I will ground this non-inverting terminal and I am applying a signal, input signal in this manner. So I am applying this in the inverting terminal. So my output here would be something like this. It will be amplified, but it will be out of phase. So, with respect to input, this is my input, this will be my output. So, when the input is given in the inverting terminal, the input and the output will be out of phase. Now, to understand the concept of non-inverting terminal, let us do the other way. We will earth the inverting terminal and apply the signal here. Initially, we applied the signal in the inverting terminal. Now, we will apply the signal in the non-inverting terminal. So, this is the input, this is my V1 and this is my V2. So, this is the voltage input at the V1 terminal. At this moment, the output will be, V out would be in phase with the input. So, of course, it will be amplified. So, the output will be in phase with the input. So, even when you are doing your practicals with your op-amp, you will have to show this, that in the inverting mode, the output is out of phase with the input, and in the non-inverting mode, output will be in phase with the input. So, in CRO, you will be able to observe the input and output in the two channels so that you can verify this output. Now, let us discuss about the voltage gain. We discussed that voltage gain of an op-amp comes in the order of 10 raised to 5 or 10 raised to 6. But this voltage gain is in fact the open loop gain, that is the gain without feedback. So, if we are giving an input of say 100 millivolt here, input is 100 millivolt, then the output would be voltage gain times the input, or AV is, we know V out by V in. So, V out is equal to AV into V in. So, AV is 10 raised to 5 and V in I have taken as 100 millivolt or 0.1 volt. So, my output voltage would be 10,000 volt. So, this is a very high value or very high order of amplification. But one thing to be noted here is, if we are using 741 IC, I said our plus VCC would be in the order of 15 volt. So, in any practical circuit, you cannot have an output greater than the biasing. That is a limiting condition. Always the output will be practically less than the biasing voltage. So, you can only expect up to a voltage of 14 volt or something like that, even if the open loop gain of an amplifier is 10 raised to 5. You will not get 10,000 volt output, then it would have been very good, but it is not practically possible. You can have only something around 13 or 14 volt, 1 or 2 volt less than the plus VCC. But theoretically speaking, you can have an open loop gain of 10,000 volt. But this is not suitable for our operations, hence our output will be limited by this. So, what we would be doing is, we will not operate this op-amp in the open loop mode, but we will operate it with feedback. That is known as the closed loop condition. So, we will give a feedback resistance RF that connects output back to the input, and this is the input resistance Ri. We will give a input signal V in here. The other terminal we will earth it. So, this configuration of op-amp is known as closed loop. The loop is closed, output is connected to the input, or this is a condition where we have applied negative feedback. So, this negative feedback will reduce the effective input and it will lead to decrease in output also. But it will have many other advantages. We have already learned what are the advantages of negative feedback. It will increase the input impedance, it will decrease the output impedance, it will increase the bandwidth, of course it will reduce the gain. So, all these advantageous properties of negative feedback can be attained here. Now, let us see into this inverting mode of amplification of op-amp in detail, and let us see what will be the output voltage in this inverting mode of amplification or inverting mode of operation. So, once again, this is the op-amp IC741, for example, is plus VCC 15 volt minus VEE 15 volt. This is the input resistance Ri, this is the feedback resistor RF. The current through the input resistor, I would like to call it as In, and this is the feedback current, I will call it as If because it is flowing through the feedback resistor. One interesting concept that you should get to understand the working of op-amp is the concept of a new word called virtual ground. Virtual ground. This is a very interesting concept and it is a must for understanding the operations of op-amp. This point A is in fact known as virtual ground. Why is it called virtual? Because A is a point that is not connected to ground. It is not connected to ground, but it has got the ground potential. That is why it is called virtual ground. So, any point which is not connected to the real physical ground, but has the same potential as that of the ground, is known as virtual ground. It is not a real ground because it is not really connected to the ground, but it has got the ground potential, so virtual ground. How will you justify this concept? We know that this point B is connected to ground. but the input impedance of this op-amp is very, very high, you know that. So, as a result, this current I in flowing from here cannot enter this op-amp significantly because of the very high input impedance. So, all the current flowing through this will be forced to go through this RF. Almost all the current, I would like to put it as I in is almost equal to IF. Only very small current in the order of say microampere or something like that would enter this op-amp, because the input impedance of this op-amp is very, very high. So, you can say that as no current is entering the op-amp, you can justify that the point A and B are more or less in the same potential. That is why no current is flowing. So, in that concept, you can call this point A to be in the same potential that of B, and B is grounded. So, A and B are now in the ground potential, and A is called the virtual ground. So, only if you understand this concept, we can understand the working of an operational amplifier. So, I have redrawn the circuit to the side. Now, let us understand this inverting amplifier in detail. How can I write this current I in? We have understood that I in is equal to IF. So, this is the basic principle behind all the operations of op-amp. I in is almost equal to IF. So, be comfortable with this concept. It is because the point A is the virtual ground, but it is not a real ground. If it were a real ground, then the current would have flown to that point through the ground, to the ground. But it is only a virtual ground, so all the current flowing through this R1 will flow through RF. So, you can write it in this way. Now, the question is, how can we write I in? I in is the current through R1. Current through any resistance is equal to the difference in potential across the two ends of the resistor by the resistance value, because you know I is equal to V by R. So, I in is equal to the voltage at this end is V in, the voltage at this end is, I will call it as VA. So, it is V in minus VA divided by R1. So, this is the expression for input current. I in equals V in minus VA by R, if I call it as Ri, input resistance Ri. Okay. Now, how can I write IF? IF is equal to the voltage at this end is VA, the voltage at this end is V out. So, VA minus V out by the resistance here is RF. So, I in equals V in minus VA by Ri or R1, whatever you would like to call it. But you know that VA is virtual ground. A is virtual ground, so potential VA is 0. So, this equation would reduce to V in by R1. Now, coming to the IF equation, VA minus V out is RF, but VA is 0. So, your expression becomes minus V out by RF. So, I in is V in by R1 and IF is minus V out by RF. Now we know that In equals IF. So let us write it in that way. In is what we got is V in by R1, that is equal to IF. IF is minus V out by RF. So what is V out by V in then? V out by V in, that is equal to, what will happen to this equation? Minus RF by R in. R1 or Rin, whatever you would have called it. I have used it in both manner. So the voltage gain with feedback, this is gain with feedback, V out by V in is equal to minus RF by R in. This is the gain of an amplifier or op amp in inverting mode. Inverting gain of an amplifier, V out by V in is equal to minus RF by R in. This is a very important expression. So be sure with the equation. So we discussed about inverting amplifier. In this case, the output was out of phase with the input, and we found that the gain of the amplifier AVF, that is gain with feedback, was minus RF by Rin, where RF is the feedback resistor and Rin is the input resistor. Now we will discuss about the non-inverting amplifier. So this is a non-inverting amplifier. We will convert this circuit of inverting amplifier into non-inverting amplifier. So we will earth this inverting terminal and apply the signal at the non-inverting terminal. So now this circuit is a non-inverting amplifier. So as the word indicates, you can guess that if the input is represented in this manner, then the output will also be in phase with the input, of course in an amplified manner. So this is a relation between input and output. Output will be in phase with the input. Now let us try to explain the gain of this configuration. So for that we will use the thumb rule, that is I input is equal to IF, or more correctly it is approximately equal to IF. So this is our thumb rule for all the derivations. So let us write what is I in this case. Before that, let us see, this point is grounded. So the potential of this end we can put it as 0 because it is grounded. What about this point of R1? This end of R1, that is the point A. You know that at the terminal B we have the input signal V in. So the potential of B is V in. So the potential of A will also be V in, because then only you can justify that no current is flowing through this. So effective potential of VA, we can take it as V in itself by the concept of virtual ground. So in order to find the current I in, we can write it as VA minus 0. VA minus 0. 0 is a potential at this end. VA is a potential at the other end. So that by resistance R1. Now this is equal to IF. So what is IF? IF is equal to V out minus VA. V out minus VA. VA is a potential at this end. V out is a potential at the other end of RF. So that divided by RF. So let us equate it because IN equals IF. So it is equal to V out minus VA by RF. So let us try to rearrange this equation. So what will you get? VA into RF is equal to V out into R1 minus VA into R1. So we will take the common factor R1 out. So R1 is equal to V out minus VA. At this point we can substitute V in for VA. We have got the justification that this potential V in will be the same potential at this point because A and B are at the same potential. So I will replace this VA with V in. VA with V in because VA is nothing but V in by the concept of virtual ground. Okay. So now we will continue this rearrangement and finally come up with what is our V out by V in. So V in into RF is equal to R1 or RI, whatever it is. I have used both the variables, V out minus V in. Now on rearranging this again, we will get V out by V in. So rearrange it, then you will get RF plus RI, or else you can use R1 itself, R1 by R1. And this is nothing but one plus R1 by R1, we will take it as 1 plus RF by R1. So this is the final expression for gain V out by V in. This we will call as AVF. It is voltage gain with feedback. So as far as this non-inverting amplifier is concerned, AVF is equal to 1 plus RF by R1. So please remember this equation. In the case of non-inverting amplifier, AVF is equal to 1 plus RF by R1, and in the case of inverting amplifier, it was minus RF by R1.